Alright, so in this video I'm just going to do one pump and plumbing problem, and it's a pretty inclusive problem, has a lot of elements to it, so it should give you a good idea how to approach any of these problems really. So let me just go ahead and kind of walk you through the problem setup here. So if you look at the problem, basically we have two tanks of water, and so each tank of water is open to the atmosphere, and then the water is starting off in this bottom tank. It's running through this short length of pipe here, going into a pump, and then it's being pumped through these two standard 90 elbows into this second water reservoir. Again, it's open to the atmosphere, and then we're given the change in the height here. So I'm going to label this as my point number 1, and this is my point number 2. So we're given the Z2 minus Z1, which is 15 meters, and then what we're interested in is determining the electrical power needed for the pump to pump water from this tank into this tank at this given setup here, where we have a change in elevation of 15 meters. So we're told over here on the right that we're using water, and it's at 20 degrees Celsius. So we use that information to look up the properties of water, the fluid properties of water, so density and viscosity. We're told the flow rate produced by the pump, which is 5 times 10 to the negative 3 meters cubed per second. We're told that the pipe is 4-inch Schedule 40 pipe, and it's made of commercial steel. And then we're told that the pumping efficiency is 65%. And then again, we're just trying to calculate the electrical power needed to pump water from tank number 1 to tank number 2 here. So first thing that we can do is cancel off the kinetic energy term here. So we're not going to have any kinetic energy effects just because the diameter of these tanks is so much greater than the diameter of the water pipe. So we're going to be able to just cancel off the kinetic energy there. We're going to have potential energy. We're going to have flow work. We're not going to have flow work because each of these tanks are open to the atmosphere. So P atmospheric minus P atmospheric is 0. So we're going to cancel off that term here. We're trying to determine what our work is, and we are going to have frictional effects. So that's the kind of basic setup. So at one point you're going to need to look up some items from tables here. So one thing that you can look up is the surface roughness for commercial steel, and then the symbol used to represent that is epsilon. So epsilon for commercial steel is equal to 0.046, so equal to 0.046 times 10 to the negative 3 meters, and you're going to find that in some kind of fluid mechanics textbook or on the internet. And then just the fluid properties of water at 20 degrees Celsius that we'll need are density. So rho at 20 degrees Celsius of water is equal to 998 kilograms per meter cubed. Viscosity at 20 degrees Celsius, go to 1.002 times 10 to the negative 3 Pascal seconds. And then you're going to need to look up in some table, again in the fluid mechanics textbook or online, to determine what the internal diameter of the pipe is, given that it's 4-inch nominal Schedule 40 pipe. So you can look that up in a table, and what you'll get, if you convert it to metric, is that the diameter is equal to 0.10226 meters. Okay, so with all that given information, we will be able to calculate what the pumping power is. So the first thing that we're going to want to do is determine what the fluid velocity is inside of the pipe diameters, inside the pipe. So U is going to equal to, well, we know from a continuity expression that Q is equal to U times the cross-sectional area, And if we solve that and substitute pi d squared over 4 in for the cross-sectional area, we get this expression, pi d squared. Okay, and then if we plug in the flow rate that we're given, 5 times 10 to the negative 3 meters cubed per second, multiply that by 4 divided by pi divided by this diameter squared, we'll get a velocity, average velocity of 6.609 meters per second. Okay, then we're going to use that velocity to calculate a Reynolds number. The Reynolds number again is fluid density multiplied by the average velocity times the characteristic length, in this case the diameter of a pipe, divided by the viscosity. Alright, and if we plug our 998 kilograms per meter cubed, our 0.609 meters per second, our 0.10226 meters, and our viscosity of 1.002 times 10 to the negative 3 Pascal seconds in for the Reynolds number, we'll get a Reynolds number calculation that yields this as our Reynolds number. And that is definitely greater than 4,000, which is implying that we're in the turbulent region. So after you calculate the Reynolds number, the next step would be to determine what your fanning and friction factor is. Since we're in the turbulent region, you're going to need to use some kind of table. You can use a Moody table or a fanning and friction factor table. And you're going to use the surface roughness, 0.046 times 10 to the negative 3 meters. You're going to use the diameter, and you're going to get a ratio of epsilon over d. You're going to use that and compare it with your Reynolds number, and then you can do a table lookup. That's going to be the way that you approach it in most fluid mechanics classes. However, there are empirical formulas that you can use, and I'll go ahead and copy and paste one that you can take a look at now. 1 second. So here's an empirical formula out of my fluid mechanics textbook. It's nonlinear, so instead of looking stuff up on a table, what I did is I wrote a program for my TI-84 that uses this relationship right here. If you're interested in that program for the TI-84, you can send me an email, and I can send you the script for the TI-84 if you know how to do any of the programming for the calculator. So I just went ahead and used that program on my calculator to calculate the fanning friction factor. It's a little bit more accurate to do it that way, and also it's quite a bit faster. So my program told me that the fanning friction factor was 0.0054. 0054. Alright, so once you know what your fanning friction factor is, the next bit would be to calculate what your frictional dissipation effects were. Excuse me. So in the last video I derived an expression for the frictional dissipation, and that was this expression right here. So we're going to use this expression. So the next thing that we want to figure out is what our L over D effective is. So if we look at our drawing here, we have a sudden contraction. So we're going from large volume to a small volume. So sudden contraction. And then we have two standard 90 bends or elbows. And then we have a sudden expansion. So sudden contraction, sudden expansion, and two standard 90s. So each of those are going to have a L over D effective. And then we're also going to have the total length of pipe, 5 plus 50 plus 15 plus 100, which is 170 meters. So what I like to do is just calculate what the total effective length is. So my L effective is equal to 170 meters plus the diameter, which is 0.10226 meters, multiplied by the quantity. And then I'm going to look up these L over D effective values. Okay, so here's the table out of my textbook here. So we have two standard 90s, so as an L over D effective of 2 times 30. And then we're going to add to that a sudden contraction. And this 4 to 1, 2 to 1, 4 to 3 is just the ratio of the contraction. So we're going to use the largest ratio. So we're going from a big volume to a small volume. So we'll use the 15 for the sudden contraction, 4:1 ratio. And then likewise, we're going from a small volume to a big volume. So we'll use the 1:4 sudden expansion, which has an L over D of effective of 30. So we're going to be 2 times 30 plus 15 plus 30. So let's go ahead and add that up. So 2 times 30 plus 15 plus 30. And that gives us an effective length of 180.74 meters. Alright, then if I solve for my frictional dissipation, I have 2 times my fanning friction factor of 0.0054 times my velocity of 0.609 meters per second squared. And then I'm going to multiply that by my 180.74 meters on diameter of 0.10226 meters. And that will give me 7.08 meters squared per second squared. And then just a quick note, meters squared per second squared is equivalent to joules per kilogram. Alright, so we're after work. We know our frictional dissipation. We know the potential energy, or it's very easy to calculate. So we can go ahead and solve for our work now. So let me just go ahead and scroll down a little bit. Okay, so what we're going to end up with is an expression that says that the negative of work is equal to our gravity times the change in height plus our frictional effect, which is equal to 9.81 meters per second squared times 15 meters. That was the change in elevation from our point 1 to point 2, 15 meters. And then we're going to add to that our frictional effect here, our frictional dissipation, which is 7.08 meters squared per second squared. And that gives us a work of 154 joules per kilogram. Alright, so it's the negative work is it's work that you have to put into the system. Positive work would be work that you can take out of the system. So you get negative work if it's a pump, positive work if it's a turbine. So what we just calculated was the ideal work, and we're told in the problem statement what the pump efficiency is, and that is 65%. We're told that the pump is 65% efficient, so this is the ideal number. So if we wanted to know what the actual work, what we do is you take the ideal and we divide by the pump efficiency. So if we do that, what we get is an actual work of negative 237 joules per kilogram. So we're not quite done yet. What we're interested in is power. So we want the electrical power for the pump needed to perform this amount of work. So if we just kind of think of a dimensional analysis for power, we know that power has units of watts or joules per second. So power is going to equal work. So we have a joule per kilogram. I need to get rid of my kilograms now, so I'm going to multiply by the density of water. So now I've gotten rid of the kilograms, but now I need seconds in the denominators, and then I also need to get rid of the meters cubed. So I'm also going to multiply by the flow rate. So the work times the fluid density multiplied by the flow rate should give me power. So let's go ahead and do that. Now power is always positive, so you just take the absolute value of your work. So 237 joules per kilogram multiplied by 998 kilograms per meter cubed, and Finally, we multiply that by our flow rate, which was 5 times 10 to the negative 3 meters cubed per second. And that will give me a total power of 1.18 kilowatts. Alright, so that is the power, or the electrical power required to pump water from our tank 1 to our tank 2. So 1.18 kilowatts to pump water from this tank up a total elevation change between the water reservoirs of 15 meters, and that's including the frictional dissipation effects of having two standard 90s, 170 meters of total length of pipe, and then also the frictional dissipation created by the sudden contraction and sudden expansion. And also taking into account that the pump efficiency is 65%. Alright, so that's going to do it for this video.